Okay, if you remember in a previous week, we discussed about the random variables, the discrete random variables. So especially we talk about the Bernoulli trial. Can someone reminds me what is Bernoulli trial or Bernoulli random variable? Alişer? So any probability experiment which has two outputs is called a Bernoulli process. Okay, and a Bernoulli random variable, it's a probability random variable which takes only two outputs, 1 or 0. And the probability of the 1 is given as a p, and the probability of 0 is given as a q. And what we want is we would like to make lots of Bernoulli processes or Bernoulli experiments, and we would like to count the different things. We can count, for example, the number of the successful trials, or we can count the number of the trials to get the successful trials. Okay, so let's do a couple of experiments. So have you ever got GPA more than 4? No? Okay, so I thought 4 is not so high, but okay, so let's say 4. If you've got 4, then this is going to be called as a successful semester. Okay, so you've got so far 5 semesters finished, right? So let's assume that before you start the learning in this university, you can count the number of the semesters you need in order to get the first successful trial or the first successful semester. For example, the two students have agreed, okay, so I'm going to get the first successful semester in the second one, and he said that I'm going to get the first successful semester in the third one. Okay, then I would like to now evaluate the probabilities. I would like to know what is the probability that he's going to get the first successful trial in the second, and he's going to get the first successful trial or semester in the third semester. So actually, the number of the semesters you need to get the first successful semester is the geometric distribution, right? It's the geometric random variable. Do you remember this? So the number of the trials you need in order to get the first success is called the geometric random variable. And if you, for example, would like to know what is the probability that you will get the first successful semester in the third semester, it is going to be the multiplication of the, so you need to create always the scenarios, right? What I'm going to do is I'm going to put 3 blocks, okay? So for every block, I'm going to put the letters, either P, either Q, depending on whether the semester was successful or unsuccessful. In order to get the first successful semester in the third semester, right? So sophomore first semester. What you need to do is you need to get Q, Q, P, right? So the Q, Q, and P. Do you understand this? That the first semester, freshman first, is failure, okay? So you've got GPA less than 4. So second semester in freshman, it's also failure. And the third semester, which is the first semester of sophomore, you've got GPA more than 4. This is the only scenario when you can get the first successful semester in the third time, when you're trying the third time, okay? And the probability of this is going to be equal to the Q in the square times the P, and this is always like this, okay? So the number of the semesters you need to get the first successful trial is called the geometric distribution. What we can do is we can still play with the number of the semesters, but let's say the number of the successful semesters is going to be more than 1. For example, let's assume that Alexander and Alisher have agreed in the beginning of the semester that Alexander can do 3 successful semesters in 5 semesters, and Alisher said that he can do this in 4 semesters, for example. Okay? Then now I would like to so who is going to do this faster, for example? Okay? So let's assume, so please note that the last semester should be successful in both of the cases, right? Because, for example, if Alexander gets the third successful semester already in the 4th semester, right? So he's going to make this in the 4 semesters. So what I want to do is I would like to evaluate the probability that Alexander can make this in 5 semesters. Exactly in the 5 semesters. Not within 5 semesters. Not at least 5 semesters. Exactly 5 semesters. So let's try to draw the boxes and simulate the scenarios. Okay? So what can be the scenario for Alexander to get the third successful trial in 5th semester? Can you help me? Oh, can you just give me the sequence of P's and Q's? PQ, PQ, P, P, Q. Is it the proper sequence of the P's and Q's? No, right? Because in this case, 3 P's, 3 successful semesters, was already in the 4, right? This is not the proper scenario. We would like to imitate this, okay? So consider all possible scenarios when Alexander can get 3 successful semesters in 5 semesters, okay? So the proper combination, the proper scenario can be PQ, PQ, and P. Right? Do you understand this? So is it the only scenario? No, we can make the another scenario, right? So 1, 2, 3, 4, 5. Can you help me another scenario? For example, P, P, Q, Q, and P. Right? And so on. So we can make the different scenarios like a Q, Q, P, 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 right? Or Q, P, Q, P, P, and so on. But it doesn't matter what is going to be the scenario. The last one is P always. Okay? And it doesn't matter what is the scenario. In all of these combinations, we've got always 3 P's and 2 Q's. 3 successful semesters and 2 unsuccessful semesters, right? So the probabilities of every scenario is going to be P cubed, Q in the power of 2 for any. Okay? Now the only question is how many different scenarios we can have. Okay? So how many different scenarios you can have? It is the number of the rearrangements of the 4 letters, actually, right? So do you remember in the beginning of the semester we considered these examples like, hey, how many different words you can create by rearranging three letters, A, B, C. What was that? 3 factorials, right? What if you got like a 4 letters, A, B, A, B? What is this? 4 factorials divided to the 2 and 2, right? This is nothing else as the same example, like a PQ, PQ, AB, AB, right? So you need to rearrange them. So you need to rearrange, put them in a different order. What is the number of the rearrangements you can make with this with this 4 letters? It is going to be 4 factorials divided to the 2 factorials divided to the 2 factorials. Well, this is going to be the probability, okay? So again, you can evaluate its probabilities by just drawing these boxes and by just putting these P and Q's. So the number of the trials you need in order to get exactly like R successful trials is called the negative binomial distribution, okay? And the geometric distribution is the specific case of the negative binomial because you're going to continue until you get the first success. And the negative binomial, you're going to continue until you'll get the second success or the third success or any number of the successful trials. Okay? Do you feel the difference between binomial, a negative binomial, and the geometric? Right? Please note that, so there are 2 things which can be constant and variable. Okay? So when you're trying the Bernoulli trial many times, so we can fix the number of the successful trials. So as we're doing for the geometric or for the negative binomial. For example, we say that, hey, I'm going to continue trying until I will get the 7 out of 9 in IELTS score. Okay? And the variable here is the number of the tries you do. Okay? Or for example, you can say, hey, I'm going to keep shooting a penalty, I will get the goal. Okay? The number of the successful trials is 1 here. Or you can say, hey, I'm going to keep trying to shoot a basketball shot until I will get the 2 shots in a row, for example. Okay? Or 2 shots in total. So in this case, again, the number of the successful cases is fixed. And the number of the trials you do is the variable. It's a random variable. Do you see this? So what we can do is we can do this vice versa. We can fix the number of the trials. Okay? So I'm going to say, hey, so what is the number of the successful semesters if you have 8 semesters? Okay? The number of the semesters now is going to be fixed, and the number of the successful semesters is going to be the variable. And this is the binomial distribution, which basically counts the number of the successful trials out of n. So what if, like I say, so far you have 5 finished semesters, right? Most of you, right? So what is the probability that you will have like 3 successful semesters out of 5? Or what can be the number of successful what can be the number of successful semesters if you have 5? How many successful semesters you can have? So from 0 to the 5, right? You may have no successful semesters, right? Or you may have only 1 or 2 or 3 or 5 successful semesters, right? You see, in this case, we are not basically changing the number of the semesters, right? Do you remember in the previous examples, so the 2 friends have agreed to get the successful semesters in a 2 semester or in 8. Now the number of the semesters is fixed, which is always 5. We're simply going to count the number of the successful trials. So now we can create a problem, like 2 friends, Alisher and Alexander, are going to make this. Hey, I can make 2 successful out of 5. And Alexander says, I can make 4 out of 5. Okay? So you see, do you feel the difference between the variables? Right? So here, this variable is called the binomial distribution. And if I would like to find the probability of having 3 successful out of 5, is going to be C 5 3 p in the power of 3 q in the power of 2. Okay? So all of this distributions can be summarized in this kind of table. And they are different by just these 2 variables. Okay? So depending on what is fixed and what is not, you can use the different distributions. So here, if the number of the trials is fixed, but the number of the successful cases is not fixed, then this is going to be the binomial distribution, right? So you always do the same amount of the trials, and then you count the number of the successful then, right? You see, so the constant here is the number of the trials. Constant is, for example, you are going to have 8 semesters. Then you're going to count the number of the successful semesters, and it's a variable. Do you feel this? This is the binomial distribution. But if you do this vice versa, for example, you say that in the beginning of all of your studies, you say, hey, I would like to do 2 successful semesters. So let's see how many semesters it takes for me to do the 2 successful semesters. And in this case, the number of the successful trials is fixed. The number of the semesters you need to do this is not, right? It's a variable, okay? So in this case, it is going to be either geometric distribution, either the negative binomial distribution. So this is almost all of the discrete distributions which we are going to consider, except the last one, when nothing is not going to be fixed. The number of the trials is not fixed, and the number of the successful trials is not fixed anymore. So both of them are going to be the variables, okay? So let's consider a couple of examples, and I'm going to try to explain you what do I mean. So let's say I went through outside, I waited 5 minutes there, and I count the number of the cars which passes through the cross road. There are 50 cars which passed in 5 minutes. So in average. So like in average, 10 cars are passing through this crossroad every minute. What I want to know is, what is the probability that there will be like 55 cars will cross this crossroad in the next 5 minutes? Okay, you see, so the number of the successful cases is actually the number of the cars which are passing, and this is not fixed, okay? It can be 0 cars, or it can be 100, it can be 60, it is not fixed anymore. The number of the trials is not fixed anymore as well, okay? Or, for example, I would like to know, so I went through to this hospital over the road, and I talked with the doctor, and she gave me her statistics. And she told me that she treats like 2 patients every Monday from 9 to 10 in average. Okay? So she had this record for many, many semesters, or many, many weeks, okay? And she counted the average number of the patients she treats every Monday from 9 to 10. And she tells that this is the 2 patients in average. What I want to know is, what is the probability that next Monday she is going to treat 3 patients? Or 4 patients, or 0 patients. Okay, you see, so it's again the random variable where nothing is fixed. So the only information which you know is the average number, right? And the number of the trials you do goes to infinity, actually, okay? So you can see this clearly with an example with the cars, okay? Do you see that this distribution is not anymore any of the previous ones which you considered before? Yeah, do you feel this? So it is not it can be binomial, actually, right? But it is not the same, because the number of the trials now is not fixed. It can be any, right? It goes until infinity. And the number of the successful trials is not fixed anymore, neither. Okay? So what I want is, I would like to derive this distribution from the binomial by just assuming that the number of the trials simply goes to infinity. Okay, let's do this together. So I recommend you to write this, because it's a beautiful proof, actually. So what we were given previously in the previous two examples, actually, the average number of the cars which passes through the crossroad, or the average number of the patients treated by the doctor in some period of time, right? You were given actually mu, or we denote this as lambda, mu or lambda. Do you remember how we calculate the expected value for the binomial distribution? Yes. N times the p, okay? N times the p. Can you tell me what is the p from this equation? Lambda divided to the n, okay? So what I want is, I would like to write down the binomial distribution formula for having k successful trials, and I find the limit of this when n goes to infinity. Okay? And let's see what we have. Do you understand what's going on? Okay. So can you remind me what is the probability of having k successful trials out of n for the binomial distribution? It was c n k, p in the power of k, q in the power of n minus k. Do you remember this? Okay. So let's expand everything here. It's going to be n factorials divided to the n minus k factorials multiplied to the k factorials times t. Instead of p, I'm going to write down n divided to the lambda divided to the n in the power of k times t. What is the q? How we can get the q from the p? Alisha? 1 minus p, right? 1 minus lambda divided to the n in the power of n minus k. Right? So I just substituted everything which we know so far. Because actually we don't know the number of the trials, and we don't know the number of the probability of having successful trial in every single trial anymore. We just know the average number. Okay? Or for example, I can say, hey, in average in Tashkent there are 2 earthquakes happening every month. What is the probability that there will be 3 earthquakes next month? You see, so you just know the average number, and we just assume that this is the binomial distribution. Okay? So we just substituted everything to here. Now I would like to do some calculations, and you need to be careful with this. So can we divide n factorials to the n minus k factorials? For example, if you divide 5 factorials to the 5 minus 2 factorials, what you get? 4 times the 5, right? So I'm going to just divide this. I'm going to write this as n minus k plus 1 times to the n minus k plus 2 until n. And this is true, okay? You can check this if you want. So, for example, if you're dividing 5 to the 5 minus 2 factorials, you should start from the 3, you should start from the 4, right? So, 5 minus 2 plus 1. Okay? And you should continue until the end. So this is divided to n in the power of k. Can you tell me where this n in the power of k is coming from? From the next term. Okay? I'm just rearranging the terms. Times t. Lambda in the power of k divided to the k factorials. Okay? Multiply 2. 1 minus lambda divided to the n in the power of n divided to the 1 minus lambda divided to the n in the power of k. And I hope that you understand what I'm doing here, right? So I just rewrote this exponential number like this, okay? Now what I want is, I would like to find the limit of everything when n goes to the infinity, okay? Because now the number of the trials actually goes to the infinity, okay? So what is the polynomial of power k divided to the polynomial of power k when n goes to the infinity? What is the limit of this? So please note that here on the numerator, you will have k terms with the n, okay? If you count the number of the terms here, it is going to be exactly the k, right? For example, if you divide 5 to the 5 minus 2 factorials, how many terms you're going to have? 2, right? 4 multiplied to the 5, okay? If you divide 7 to the 7 minus 2 factorials, how many terms you're going to have? 2. 6 times the 7, right? So 7 factorials divided to the 5 factorials is 6 times the 7, right? So if you divide n to the n minus k factorials, you're going to have k terms in the numerator. It is the polynomial of power of k, right? The highest term of this polynomial is n in the power of k, and you're still dividing this to the another polynomial of the k's degree, right? What is the limit of this ratio when n goes to infinity? 1, right? Do you remember this? Like, for example, n squared plus 2n divided to the n squared is going to give you 1. The second term here doesn't have any terms connected with the n, so that is why its limit is itself. So what is the limit of this term here? So lambda is the finite number and the k is the finite number. Okay, they're fixed. There are some finite numbers. They cannot be infinity. So the lambda finite number divided to the infinity is 0. 1 minus 0 in the power of some finite number is going to be equal to the 1. Okay? So this limit is equal to the 1. So this limit is equal to the 1. But this limit is not 1. So when n goes to the infinity, it is going to be 1 minus some finite number divided to the infinity in the power of infinity. Okay? It is not 1 anymore. And if you remember from calculus, this is e in the power of minus lambda. Okay, there was a limit which we use a lot in the compound interest formulas. So it was 1 minus or plus 1 divided to the n in the power of n is simply e. Okay, then you can just use that limit in order to prove that 1 minus lambda over n in the power of n is equal to the e in the power of minus lambda. Okay, actually it was a definition of the e. So the definition of the e is the limit of n goes to the infinity, 1 plus 1 divided to the n in the power of n, it's e. So by just using that formula, we can prove that this is equal to the e in the power of minus lambda. So what is left when n goes to the infinity? So the lambda in the power of k divided to the k factorials times the e in the power of minus k. Or minus lambda, sorry. Right? This is what is left. Okay, when n goes to infinity. And we call, and this is going to be the distribution. So do you see? So that we've got this from the probability of having k successes in n trials when n goes to infinity, right? Do you remember I told you, hey, what is the probability that next 5 minutes there will be 55 cars, 55 successful trials, when the number of the trials is infinity, okay? And this is equal to this value. So you just need to substitute the average values here and the number of the successful trials in order to get the value. And we call this distribution as the Poisson distribution. Okay? So when you are given the number of some events happening in some period of time, and you would like to evaluate the probability of another number of the events in the same period, we are going to use the Poisson distribution. Okay? So the probability of having k successful trials in this case is going to be e in the power of minus lambda times the lambda in the power of k divided to the k factorials. And actually, you should always know that the Poisson distribution is the approximation of the binomial distribution when n is large and p is small. Well, have you ever heard about the life insurance? Yes. So in Uzbekistan as well, in many other countries in Europe, so you can insure your life. Okay, you pay some amount of the money to the insurance company, and then they're going to compensate if something happens. Okay, so let's look to this problem from the perspective of the insurance company. Okay, insurance company believes that the probability that 30 years old male survives within a year is very high. It's actually 0.9986. So what they do is they would like to sell a policy. So the policy is an insurance paper policy for $161. And they sold this to 1,300 persons. And they collected, say, 1,061 times the 1,300, roughly $210,000. So now, and if something happens, if a person doesn't survive, then the company should pay $100,000 compensation. So after 1 year, if everyone survives, then the company is going to have a lot of profit, right? 210,000. If there will be only one person who is not going to survive, then the company still is going to some profit, right? And it's going to be 110,000. If two persons is not going to survive, company is still going to be in profit, right? So what I want to know is, what is the probability that company will be in profit after 1 year? Okay, so depending on this, we can make some calculations, right? For example, if the probability that the company will not be in a profit is lower, for example, right? Then we can increase the price of the policy. Okay, so let's do this together. So what we need to do is we need to find the probability that the company will have a profit using the Poisson distribution and using the binomial distribution, and compare the two results. So in order to do these calculations, so please note that you're given here many things. So you can calculate the binomial distribution, by the way, because you're given n, the number of the trials, right? So there are 1,300 people, there are the n. And you're also given the p, right? So what is the p here, by the way? So this is not a p. So the p probability that a person will not survive or will die is 1 minus this number, right? And it's going to be 0.0014. That's the p. And also, in order to calculate those probabilities using the Poisson distribution, we need to know the average number of the people, average number of the 30 years old males who are dying with this probability, right? So can you tell me what is the expected value, expected number of the people who will die within 1 year? How to calculate this? If you're given the n, the sample size, and if you're given the probability that every person will die, for every person, the probability, what is the expected number of the dice? It's going to be NP. Do you remember the formula, right? Okay, so I hope that you understand this, right? Mu. So mu was n times the p. Probability that a person will die is 0.014, and the average number of the people will die is simply 1 minus p times the n, which is going to be 1.82. So just using this, we can evaluate the probability that company will be in profit. Let's assume that X is going to be the number of persons who won't survive. So up to which number it should be, so what is the maximum value of the X so that the company will be in a profit? So the company will be the profit if X is less or equal than the 2. Right? If X is equal to the 0 or 1 or 2, still the company is in the profit. Right? What we need to do is we need to evaluate the probability of X is equal to the 0, or X is equal to the 1, or X is equal to the 2. Right? Because if you remember, if no one dies, then the company will be in a huge profit. Then if one person dies, the company will be still in profit. 2, still in profit. If 3 persons die, the company should pay 300,000. They've actually collected 210,000. They're going to be in the negative, right? Minus 90,000. So let's evaluate this using the Poisson distribution. Do you remember the formula for the Poisson distribution? It was e to the power of minus k, or minus mu, times the mu in the power of k divided to the k factorials. So if k is equal to the 0, what you get from this formula? Or lambda, e to the power of minus lambda, right? If k is equal to the 1, what you get? Minus lambda times to the 1, right? Plus, if k is equal to the 2, it's going to be e to the power of minus lambda times to the lambda in the power of 2 divided to the 2. So times to the lambda here, by the way. I'm sorry, maybe this formula is confusing for you. So e to the power of minus lambda times the lambda in the power of k divided to the k factorials. Mu and lambda are interchangeable variables. Okay? So now I'm just going to make the calculation. It's super easy. You just need to use a calculator. So the e in the power of minus lambda that can be taken out from the brackets. It's going to be 1 plus lambda squared over 2. So e in the power of minus 1.82 times 2, 1 plus 1.82 times plus 1.82 in the square divided to the 2. What is this? 0.72, right? 0.725. It can be more than 1, okay? If you've got more than 1, it means that you did the mistake because the formula is correct, okay? So the probability the company will make a profit is actually 72.5%, which is high actually, okay? So what I wanted to do is I would like to evaluate the same probability using the binomial distribution and compare the result. Actually, you see, so calculating the Poisson distribution is very easy. You just need to know when to use the Poisson distribution, okay? This is the most difficult part, I would say. So let's try to do the same with the binomial distribution. For the binomial distribution, what you need to know is, you need to know the number of the trials. You need to know also the number of the successful trials, right? In this case, the successful is the persons who are not going to survive, okay? So let's evaluate this. So what is the probability of x is equal to 0 using the binomial distribution? It is c n 0, p in the power of 0, q in the power of 1,300, right? Or n, okay? It is going to be 1 times the 1 times the z. Q in our case is 0.9986 in the power of 1,300. It's actually a very realistic problem. People from the insurance company do similar calculations, by the way. Yeah. 0.16. Okay? What is the probability of x is equal to 1? Just using the binomial formula, I'm going to use the c n 1, p in the power of 1, q in the power of n minus 1, right? I'm just going to put down everything into this formula. It's going to be c 1,301, p in the power of 1, q in the power of 1,299. It's going to be 1,300 times this is 0.0014 times this is 0.9986 in the power of 1,299. 0.29, okay? So probability of x is equal to the 2. It's going to be c n 2, p in the power of 2, q in the power of n minus 1. If we put all of these numbers and we calculate n, c of n and 2, it's going to be n factorials divided to the n minus 2 factorials divided to the 2 factorials, right? It is going to be 1,300 times the 1,299 divided to the 2, okay? This is the c 1,302 times 2, 0.0014 in the power of 2 times the 0.9986 in the power of 1,298. 0.26. Can you add the three values? Probability the company will be in a profit is x is smaller than 2. It's the sum of these numbers, 0.16 plus 0.29 plus 0.26. What is this? 0.72? It should be 72 because we didn't put the values here. Okay? If you calculate this a little bit more precisely, you're going to get 0.72. Very close results. And you see, the calculating this using the binomial distribution, especially when n is huge, is very difficult. Okay, so here it was very kind of easier for us to calculate this value because this value was small. Okay, so if n is huge, for example, if n is million, and you need to calculate the number of the successful trials, for example, n is so k is equal to the 10, it is going to be difficult to calculate this already, at least manually, okay? So we can easily approximate the binomial distribution using the Poisson distribution when n is large, okay, and p is small. So this is exactly the case when p is small, right, 0.0014, and n is large, 1,300, okay? And then we can use the Poisson distribution. Okay, so let's make a summary of all of the discrete distributions which we've learned so far. So this is going to be a cheat list for you, so you can use this table in order to make calculations or solve the problems. So we talked about the binomial distribution, geometric and negative. So we're going to fix one or the another type of the variables, right? Or the number of the trials, or the number of the successful trials. And the Poisson distribution is nothing is fixed. So the number of the successful trials goes to infinity, number of the trials also goes to infinity. And here are the probability mass functions which we are going to use. Okay, so all of this, so these are the main discrete probability distributions. So from this week, we're going to start talking about the continuous case. The continuous case is going to be slightly difficult, or different, I would say, and difficult as well. So if you remember, in a discrete case, the probability mass function is given as the dots when you graph this, okay? Because the discrete random variable has specific values, and as a rule, it has the finite number of the values. For example, if x is the number of the absences per semester, its value is fixed. It is always going to be between 0 and 16, for example, right? And it can take the values 1, 2, 3. It never can take the value between 1 and 2, or between 2 and 3, okay? Or if the number of the lectures when your professor is late, it's also a discrete variable, right? And we always put this using the dots. And then we can play with these variables, right? For example, I would like to know what is the probability that your professor will be late for more than 4 lectures in the semester, okay? It is going to be the binomial distribution because the number of the trials is fixed. You can calculate the probability of being late for your professor for every lecture, right? Just using the previous history of being late of your professor and so on, okay? So what we need to do is now we need to talk about the continuous random variables, okay? So here in this graph, so x-axis means the values of your random variable, y-axis means the probabilities. So now let's talk about the continuous case. So if I would like to now simulate the amount of the time when your professor is late, it is going to be a continuous random variable. It is not discrete anymore because I measure the time, right? And it can be any time, for example, like starting from 5, there are infinitely many values for this x, okay? It can be 1.5 minutes, or 1.555 minutes, or 1.555 minutes, right? You see, it's a continuous. I can't really put the points anymore. Previously, if I need to calculate the probability, I just put the point in this graph, and that's going to be the probability. Now it is not. Okay, and I can't really describe the probabilities for this random variable using the points because then I have to use infinitely many points. So what we're going to do is we are going to describe such a continuous variables using the curves. And we call the curve of the continuous random variable as the density function. So the probability function for the discrete is called the mass function. And the probability function for the continuous is called the density function. There is an explanation. We're going to discuss this at some point, okay? So let's today talk about the density function. The density function explains us the continuous random variables. So now, previously, in order to calculate the probability, you just pick one of the values of your function. Now you can't really do this, okay? So we are going to evaluate the probabilities of the continuous random variables by just finding the areas under the density function. Okay? For example, if I would like to know what is the probability that your professor is going to be late between 5 and 10 minutes for the next lecture, what I have to do is I need to find this point 5, then I need to find this point 10, then I need to evaluate this area. This area is going to be the probability. Okay? So this density function is f of x, let's say. Then this probability is going to be the integration of the f of x from 5 to the 10 with respect to the x. Okay? So this is how we are going to evaluate the probabilities in a continuous case. And you can expect that this is going to be a little bit different from this discrete case. Okay? So if you already forgot all of the integration methods, you need to go and review them a little bit because we're going to do a lot of integrations, actually. Okay? So before we proceed to actually calculating the probabilities for the continuous case, I would like to give you a couple of rules. Okay? So what is actually the proper density function? Do you remember we discussed about what is the proper mass function a little bit? So we are going to define the properness of the density functions as well. Probabilities between A and B is going to be found by finding the area. And do you remember what was the amount of the total probability? total probability. So in the mass function, what is the sum of all of the probabilities? 1, right? So the same is here. Probability that your random variable x is between minus infinity and plus infinity should be equal to 1. Okay? So the total area under your density function, under your density curve, should be equal to 1, so that it is going to be a proper density function. So you find all of this area, and this area should be equal to 1, from minus infinity to the plus infinity. So if you would like to find the probabilities, we are going to find is by evaluating these areas. Okay, it's super important to know how to make the integrations in order to evaluate the probabilities now. And now, if you would like to evaluate the probability at a single point, so what is the probability that your professor is going to be late exactly 5 minutes next lecture? Just using the theory, we can evaluate this using the integration, right? Can you help me? So what is the probability that your professor is going to be late exactly 5 minutes? That is going to be an integration of this density curve from 5 to the 5. What is this? 0, right? It's always 0, okay? Because if you remember the Newton-Leibniz formula, you have to find the antiderivative, right? Then you need to find a b and a. Do you remember? So if the two values are the same, then obviously your integration is going to be 0, according to the Newton-Leibniz formula. Okay? So according to our algorithm, we are going to find the probabilities by finding the integration. Okay? And the algorithm tells me that I cannot evaluate the probability at the single point anymore. And this is one of the properties of the density functions as well. So if someone is asking you what is the probability that your continuous variable is going to take exactly one specific value, it is simply going to be equal to 0. Because the integration between these two values is going to be equal to 0. Okay? So you can approximate this by taking the epsilon, right? You can take the small distance in here and small distances there, and you can find the integration, okay? Probability at the single point for the continuous random variable is equal to 0. There are 3 properties. So let's do a small exercise. Suppose that x is a continuous random variable whose probability density function is given like this. So some constant c times the 4x minus 2x in the square. X can change between 0 and 2. Otherwise, it is going to be simply 0. Okay? You can assume it's curve. It's 0 until 0. Okay? Then it's going to be some curve until 2. Then after 2, it's again 0. Okay? So the c should be a specific value. It can't be really any value. Okay? It can be huge or it can be 0, for example. Okay? So what is the value of the c so that this is going to be the proper density function? Okay? We need to evaluate the c first of all. Then in the second problem, we need to evaluate the probability that x is greater than 1. Let's do these 2 exercises. So if I would like to evaluate the value for the c, what I have to do is I need to integrate this function, right? The integration of this curve f of x from minus infinity to the plus infinity should be equal to the 1, right? And if you remember from calculus, you can split the integration into the parts. For example, from minus infinity to the 0, f of x dx, plus from 0 to the 2, plus from 2 to the infinity. And the reason why I did this because my function is defined at piecewise. Okay, it is defined from minus infinity to the 0, from 0 to the 2, and from 2 to the infinity. Okay, and then I'm going to now substitute the values of the f. So the value of the f in this interval from minus infinity to the 0 is 0, and from 0 to the infinity is also 0. And the value of my function between 0 and 2 is given like this. And I'm just going to substitute this there. That's going to be integration from 0 to the 2, c times the 4x minus 2x in the square dx. Can you help me with evaluating this integration? In order to do this, we need to know the antiderivatives, right? So it's going to be c times the 2x squared over 2, right? This is the antiderivative of the 4x, minus 2c times the x cubed over 3, which is going to be the antiderivative of the x squared. Okay? Then we need to substitute 0 and 2. It should be 4 here. Okay? So please know that if you substitute 0, it's going to be 0. So I'm not going to substitute the 0. I'm just going to substitute the 2. If you substitute the 2, it's going to be 4 times the 4 divided to the 2. It's 8, right? 8c minus 16 over 3c, right? 16 over 3c. If you give the common denominator, it's going to be 8 over 3, right? 8 over 3c. And this should be equal to the 1 because we started from this integration, right? And from here, we can find that the value of the c should be equal to what? 3 over 8. For exactly this value of the c, this is going to be the proper density function. For any other value of the c, the area under this curve is not going to be equal to the 1. So that is why it can't be really the proper density function. Okay? So now, when we've got the proper density function, we can evaluate the probabilities for this random variable. But again, we need to do the integrations, okay? So now we know the shape of the proper density function. It is given as 3 over 8 times the 4x minus tx in the square. And if I would like to evaluate the probability of x is greater than 1, what I have to do is, oh, by the way, what is the difference? Is it different to evaluate that x is more than 1 or more or equal to the 1? In a continuous case, it doesn't matter anymore. In discrete, it is important, okay? In continuous, it is not. Because we know that the probability at the single point is equal to the 0. Right? So you have to evaluate this integration from 1 to the infinity, actually, right? But since we know that after 2 it is equal to the 0, I'm just going to simply write this from 1 to the 2. Oh, by the way, since this interval from 1 to the 2 is exactly the half of the interval between 0 and 2, is it the probability going to be 0.5? No, I mean, not necessarily, right? Because your curve can be different, right? Your curve can be triangular, for example. If your curve is like uniform, just a line, then yes, okay? But if your curve is different, then not necessarily. We need to still evaluate this. 3 over 8, 4x minus 2x in the square. I'm going to find its antiderivative. It's going to be 3 over 8, x squared over 2x in the square, right? So minus 2 over 3 x in the cube. And I have to evaluate 1 and 2. If you put the 2, it is going to be equal to 1, by the way, right? Do you remember? I mean, it's 1 for sure. Because we've just evaluated this. We've chosen the c to be equal to the 3 over 8, so that when you substitute the x to be equal to the 2, it's going to be 1, right? Now let's substitute the 1. Minus 3 over 8 times the 2 minus 2 over 3, right? It's going to be 6, 4 over 3, 1 over 2. It's going to be 1 over 2. Is it 1 over 2? Okay, but this is just by coincidence, okay? So this is the first time when I'm solving this problem. Also, I didn't expect that it is going to be 1 over 2. Otherwise, I wouldn't ask you that question in the beginning. But okay, it's 1 over 2. Okay? So this is the introduction for the continuous random variables. We're going to evaluate this differently using the density functions and integration. So in our next lectures, we're going to discuss about the properties, like how to find expected value, the variance, and also about the specific continuous random variables. Okay? Okay, thank you very much. See you next week. We need your IDs for colas. Very fruitful day, I would say.